Hi everyone! In this cartoon, we'll learn about the basics of motion capture in computer graphics and how it works. So, specifically, we'll cover the motivation behind motion capture and the general terminologies or equipment used in motion capture. Now, here are some related terminologies. Motion capture is what we'll be going over today, and we'll talk about skeletons and bones that make up skeletons. And we introduce what degrees of freedom are, and we'll talk about frames in motion capture. So keyframing is a classic animation technique, and in Keynote and PowerPoint, we're able to use magic move or morph to interpolate the frames in between to create simple animations like this. However, the robot arm has only 3 parts that need potential adjustments in each frame. For more complex models used in this video demonstration, it would be hard to create all the keyframes for animations manually given so many adjustable vertices. And that's where motion capture comes to the rescue. Motion capture is widely used for creating animations or special effects in games and films. Observe how the motion of the actor is captured and applied to the model in film. The dots on the actors are the reflective markers, and with the help of IR or infrared illumination and cameras, the motion data can be captured. So how do we perform motion capture? We can actually break it up into 3 parts: rigging, skinning, and capturing motion. Let's start with rigging. Rigging allows us to model the body movements of a character. In this diagram, the objective skeleton gives us control over the character and allows us to easily change its pose. It usually uses hierarchical modeling, as shown in this video. But just having skeletons is not enough, so after we have a skeleton, we want to add a nicer looking mesh or skins to make our model look better. And using weight calculations, we can translate the points on the mesh according to when the skeleton bones and joint positions change. An important terminology for both rigging and skinning is the degree of freedom, which is the set of independent displacements and/or rotations that specify completely the displaced or deformed position and orientation of the body. In other words, we are asking the questions: can a joint translate in X, Y, and Z? And can a joint rotate in X, Y, and Z? Giving us the maximum degree of freedom of 6. Each joint can have different degrees of freedom based on how the skeleton works. Finally, how do we capture motion data from the real world? With all the equipment for optical motion capture ready, marker positions will be recorded over a period of time and help us estimate the joint locations based on some algorithms so that the recorded movements could be applied to a skeleton later. In fact, motion capture data has frames that are very similar to pixel frames from a video taken from a camera. It's just that each frame now stores the position and rotation values for every joint in the skeleton. In addition to traditional motion capture methods, Markerless motion capture is a new technology as shown in this video. Note how no IR markers are used, and the computer infers joint positions and rotations from footage taken with a traditional camera. Now you know the basics of motion capture in computer graphics. Thank you so much for watching.